it will often be the case that we have a mixture of gases. And so we want a way to be able to represent the properties of the gases combined or individually. So we're going to define something called the partial pressure. This is going to be the pressure of the gas if it just existed by itself in the container. So in this case, the partial pressure of the green molecules would correspond to if this blue molecule wasn't present. Now the total number of molecules, that's going to be N, and here 2/3 of all the molecules are the green molecules. So the partial pressure is just going to be 2/3 of however many moles are in the container, plugged into our PV equals nRT equation, so times R times T divided by V, which is going to be equal to 2/3 times nRT over V, which would be the total pressure. So we have 2/3 times the total pressure. And now for our other substance, 1/3 of all the molecules correspond to that substance. So the total number of those molecules is going to be 1/3 of N. So likewise, we plug that into our equation, and that's going to be the same as multiplying our total pressure, which is nRT over V, by 1/3. So it's 1/3 of the total. Now these are called the mole fractions. The moles of A over the total moles and the moles of B over the total moles. And 2/3 plus 1/3 gives you 3/3. So if we add this pressure to this pressure, we should get back the total pressure inside the chamber, the pressure that we would have calculated if we just took all the molecules in, multiplied by R and T, and divided by V. So this leads us to a useful conclusion called Dalton's law of partial pressures. Now we're going to state it in two ways. We are going to state it in the way that we came up with, that the pressures all added together give us the total pressure. And we can also state it as any individual pressure is going to be equal to the mole fraction, the number of moles of that substance, divided by the total moles in the container, times the total pressure. And these are two different ways of stating Dalton's law of partial pressures. But on the whole, they mean the same thing, that we can figure out individual pressures based on what proportion of gas is represented by that individual substance. Let's say that we have a sealed vessel of some kind, and inside this vessel we figured out we have 5 moles of carbon dioxide gas and 8 moles of oxygen gas. And we measure the total pressure inside of this container, and we measure 842 torr. So then what are the partial pressures of the CO2 and the O2? Well, according to Dalton's law of partial pressure, the pressure of any individual gas is equal to its mole fraction times the total pressure. So the mole fraction of carbon dioxide is going to be the 5 moles divided by the total moles, which will be the 5 plus the 8 from the O2, and then times the total pressure. Now we multiply that out, get 324 torr. And the same thing for the oxygen. Now the oxygen was 8 moles out of our total of 5 plus 8 is 13. And we multiply that by 842 torr, which is our total pressure, and we get 518 torr. Now if we add these together, by Dalton's law of partial pressures, they should add up to the total. So that's a check on our answer. And if we add these together, we get 842. So apparently our math was correct here. As another example, let's say that we have injected a container, a 3-liter container. We have 6 grams of krypton gas and 4 grams of hydrogen gas. And this is all at 5 degrees Celsius. What are the pressures of the krypton and the hydrogen? What's the total pressure? Well, first thing that we're going to need is to convert from grams into moles. So that's what our ideal gas equation uses, is the number of moles in the container. So 6 grams of krypton divided by its molecular weight of 83.8 grams for every 1 mole, according to the periodic table, gives us our 0.0716 moles of krypton. And hydrogen, we take our 4 grams and divide by its total weight of 2.02 grams, because there are 2 hydrogens for every 1 mole. And that works out to 1.98 moles of hydrogen. Now that we know the number of moles, we can plug in to our ideal gas equation, PV equals nRT. We're given the temperature and the volume, and R is a constant, so we have everything that we need. So we can start by doing this for krypton. So we plug in our 0.0716 moles for our moles of krypton. We use our ideal gas constant. We use our temperature. We need to convert that into kelvins. So add 273.15 to our 5 degrees Celsius. And our volume was 3 liters. Now if we want to check our units here, moles here cancels out, kelvins here cancels out, liters here cancels out, and we're left with atmospheres, which is good because we're looking for a pressure, so we better get units of pressure. And we multiply all the numbers and get 0.544 atmospheres. Now we need to do the same thing for our other gas in our container, the hydrogen. And it's the exact same setup. The only difference is that now we have the 1.98 moles of hydrogen in our container, but same R, same temperature, same volume. And that works out to 15.1 atmospheres. So the fact that hydrogen is a much lighter molecule and we get a lot of hydrogen for those 4 grams compared to not so many for the 6 grams of krypton makes a big difference in the ideal gas formula. Now the total pressure is just going to be the sum of these two pressures from the individual gases. So we'll add the pressure from the krypton and the pressure from the hydrogen, and we get a total of 15.6 atmospheres altogether. Well, there's an important question that we haven't addressed so far. It's an experimental question. So we're generating all these different gases from our reactions. How are we actually going to isolate those gases and measure them? That can be tricky. If we're trying to transfer substances in the laboratory between containers, we have to worry about air mixing in. So how are we going to exclude those air molecules? Well, the trick is going to be in our apparatus. So what we're going to do is we're going to perform the reaction in some sealed container. And so this reaction is evolving gas. Now the gas is going to go through a tube. Over here we have an inverted beaker, and the gas molecules will bubble up into the beaker, and as they do so, the volume will push out water. And the water is free to leave this container, but the gas is not going to leave the container because it's more buoyant than the water is. So it's going to remain up here and the water is going to get pushed out. Now because it can be pushed out, it's going to equilibrate with whatever the pressure is outside of it. So however much the external air is pushing down, is going to be matched by how much this is pushing down. So they'll reach equilibrium. So we can use our barometer that we have in the laboratory somewhere else, and whatever pressure we read in that barometer is also going to be the pressure in the container. Now if we take the temperature of this water here, then that's going to match the temperature of our system. And so now we know the volume based on the markings on this container. We know the temperature. We know the pressure. That's everything that we need in order to calculate the number of moles of gas in this container. Now unfortunately there's a catch here. And a catch comes from the way we've set this up. We've set this up using water, and water evaporates. So there's also going to be some water particles, some water gas, mixed in with our other gas, whatever it is. So what are we going to do about that? Well, it's actually pretty straightforward because of Dalton's law of partial pressures. Dalton's law of partial pressures says that the total pressure, which we know, is equal to the sum of the pressure from the water vapor plus the pressure from any other gases. So we can actually just subtract the pressure from the water. And how do we know that? We just look it up in a table. So this is going to depend on the temperature. And so we'll have to consult our chart for whatever temperature we're at and see what the vapor pressure of water is at that temperature. But once we look it up, then we can just subtract it from the total pressure, and whatever remains is the pressure of our gases in our container. All right, so now let's do an example where we're performing a reaction over water. That's going to be the key term. Whenever you perform these reactions over water, you have to take into account the pressure from the water vapor. This is going to be a little bit more involved of an example because we are going to pull together our stoichiometry as well. So what we know, we have our system set up like we described. And when we perform this reaction in our Erlenmeyer flask, we bubble the gases produced into our inverted beaker underwater. 125 milliliters of volume is displaced by the O2. So that's the total volume of all our gases. But there's also going to be some water gas in there. And we measure our thermometer, that is 26 degrees Celsius. And we look at our barometer, measure 765 torr in the laboratory. The gases are going to equilibrate to this pressure, so that's also going to be the pressure inside of our system. Now our question is not about the O2 though, it's about the KCl3. How much KCl3 was decomposed? So our strategy here, what we're going to need to do is we're going to need to use our knowledge of Dalton's partial pressures to separate out the component of this pressure which comes from the O2. So we do that by getting rid of the component that comes from the water vapor. Once we know the amount of pressure it's from the O2, then we can use our ideal gas equation to figure out how many moles of O2 are present. And once we know that, then we can use our stoichiometry to convert from moles of O2 into moles of KCl3. And our final step, as always, will be to convert that into a mass. So let's go ahead and start by figuring out our pressure. And we'll do that by taking our total and subtracting the pressure from the water. And we look this up in our table, and it turns out that at 26 degrees C, it is 25 torr. So take our 765 torr minus 25, get 740 torr. So that's the pressure of just the O2 gas by itself. Now we can figure out the total number of moles of O2 using our PV equals nRT equation. So solving for N is going to be PV over RT, and then we'll plug everything in. And here I've done it in a single step. So I converted the pressure from torr into atmospheres. Has to be in atmospheres because R is in atmospheres. I converted our milliliters into liters, 0.125 liters. Converted our temperature into kelvins. And so now kelvins will cancel, atmospheres will cancel, liters will cancel. And we divide by moles twice, since we divide here and then we divide that. And so that's going to flip moles up in the numerator. So we're going to get units of moles. That's good. That's what we wanted to find. Works out to 0.00496 moles of O2. Now that we know about our O2, we need to convert that information into information about KCl3. And the way we convert information about substances from one substance to another is always using stoichiometry. So we need to start with our balanced reaction, which was given to us. 2 KCl3 gives us 2 KCl and 3 O2s. And we can use that to get from moles of one to moles of the other. So take our 0.00496 moles of O2, and for every 3 O2s, we get back 2 KCl3s. So multiply by that ratio to get rid of the O2 and get KCl3. You get 0.00331 moles of KCl3. And then our final step is the usual, because we can't really measure moles in the laboratory. We can only measure masses. We're going to go ahead and convert this back to grams so that it makes experimental sense to us. And so multiply by the molecular weight of the KClO3, and moles will cancel, and we will get 0.405 grams of KClO3. Now just a quick review of what we did. We had oxygen gas and water gas in our system because our reaction was performed over water. So we subtracted away the pressure from the water gas, leaving just the pressure from the O2. Then we used PV equals nRT to take that pressure of O2 and convert it to moles of O2. And then we used our stoichiometry to convert from moles of O2 into moles of KCl3 and converted that into a mass.